All right, we're going to talk about array-based trees. And what we're going to find out is we can get some of the benefits and behavior of a tree and an array at the same time using this array-based tree. So for example, if you wanted to do a breadth-first traversal or search, you could store your items in an array-based tree. Okay, so before we talk about the array-based tree, let's talk about what that means to be depth-first or breadth-first. Okay, let's start with a depth first traversal. This is actually the one, we know about this one already. Our in-order, pre-order, and post-order are all depth-first searches. So imagine we had a tree that looks something like this, where these are our nodes. All it means to be a depth-first traversal is we go down the tree first, right? We go depth-wise, and then we come up a little, and then we go down, and we come up, and then we work our way down here. So it's always a kind of a down and up type of traversal, or if we're doing a search. Now, breadth-first is more of a side-to-side, okay, all at the same level. So let me draw the same tree. Okay, breadth first wouldn't go down and up. You'd handle all these first at that level, and then all on that level, all on that level, and finally all on that level. Okay, so I said with an array-based tree we can do these breadth first traversals pretty easily. We can also do it with a classic binary search tree. It's not like it's impossible to do this type of traversal with a binary tree. Basically, we have to handle each one of the levels in a separate call to a function. So let me show you some code here that would this would definitely do a breadth first traversal of a binary search tree. So the first step is to find out the height of the tree. Okay, so the height might be 1, might be 2, might be 10. Right? And the idea is we're going to have a variable to keep track of the current level. So we'll start at 1 and we'll go up to and including the height of the tree. Okay, then down here we're going to call this print@level function, and we're going to basically through each iteration we're going to tell print@level which level we're interested in. We also have to tell it our current level. This will make a little more sense in a second, where we always start at level 0, okay, or basically ahead of the very first level, and then we always start at the root. This is pretty typical. This is a pretty typical recursive tree-based function. So again, we're passing in the desired level, our current level that we're currently on, and a node pointer to a node. So every time we call this function, we increase the current level. So that's why, remember, I started at 0. 0 is not a real level number. I'm saying all my levels start at 1. So the very first time we call the function, we're passing in level 0 and the root pointer. Okay, so this should be increased to 1. And now we check to see, well, is that the level? Is the current level actually the desired level, the one that the user wants us to print out? And if so, we'll just go through we'll use the pointer, pcurrent, to pull out the data. Okay. Now, if this was not true, so we're not at the desired level, what we'd want to do is recursively search down into the tree. So we'd call print@level again, right? This time our current level has been increased by 1, so it'll be increased again next time we recursively call this function. And then of course we pass in a left pointer and a right pointer. So this will traverse the entire tree up until we get to the desired level that we're at. And only if we're on the desired level will we actually print the data. It'll skip, kind of still process the layers above, but only print out the layers at or the data at the desired level. Okay, so this will definitely do a breadth first traversal. Let me draw a tree, and then maybe we could walk through that a little bit more. Let's say we wanted to insert the values 42, 17, 24, 13, 15, 50, 44, and 46. Okay, so if we were going to insert these values in a plain old binary search tree, when we insert the value 42, that of course is going to go at the root. Okay. Next, when we enter 17, 17 is less than 42, so we know the 17 would go here. When we insert 24, 24 is less than 42, but it's greater than 17. So the 24 would go there. 13 is less than 42, it's less than 17. Okay, 15, we'd go here. Okay, less than 42, less than 17, greater than 13. And then we hit that null pointer. 50 is greater than 42, and we'd hit that null pointer. 44 would land here. And 46 is greater than 42, it's less than 50, but it's greater than 44. Okay, so this is what our tree would look like if we did these inserts. Okay, and basically what we have to do is think about the levels. Right? The height of this tree is what, 4? So there's, we'll call this level 1. It's level 2, level 3, and level 4. Okay, and notice, just kind of notice the number of items that are potentially at each level. So we had, on level 1, there's at most 1. On level 2, there's 2. On level 3, there's room for 4 items at this level. And at level 4, there's actually room for 8 items. These are all powers of 2. And in fact, at any level, let's say level n, we have 2 to the n minus 1 potential items could be stored on that level. Okay, so back to our breadth first search. Basically, we're going to, for each of the levels 1 through the height of the tree, we're going to call print at level starting with the root. Okay, so starting at level 1, we are going to print out 42. Right? Then the next iteration of that loop, level will be equal to 2, and we have to again always start at level 0, or basically the root. And now what's going to happen is current level is going to be 1. That's not the desired level of 2, so we're going to recursively go left, and of course we're going to increase the current level. So we're going to process that one, and then we're going to return to where that was called and go right. So we go left, and then we go right. And we will have processed that level, and so on. So at level 3, we'd kind of bypass the top part of the tree and traverse here all on this level, and then similarly on level 4, we get through those. Okay, so we can definitely do breadth first type searches with a binary search tree, but I wanted to talk about array-based trees, and it turns out we can do something very similar with an array-based tree. So let's kind of look at the levels here. Okay, so we already talked about the fact that at level 1 we have 1 item, 2, 4, 8, and so on. Well, we can draw a picture where instead of having left and right pointers, maybe we'll think of these items as being in an array. Okay, so let's say our first value, remember, was 42. And then we had 17 and 50. Okay, then we had 13, 24, 44. And then we kind of had this empty slot, right? If we go back to this original one, there was room for an item here, but we never really used it. Okay, same down here. There was room for 1 here, and there was room for 2 here. But they just didn't happen to be used. If there was 1 here, there would be room for 2 more down here. Right, so there's 1, 2, 4, 8 potential items at this level. Okay, so this one was empty. 15 was, well, I think, to the right of 13. Then we had a few empty slots. And then 46 was, again, I think, to the right of 44. And then we had these 2 empty slots were kind of to the left and right of this one here. Okay, so let me just draw some numbers underneath each one of these boxes. And you can see that this could very easily just be a plain old array. Okay. In fact, let me draw that out. Okay, so this picture up here is the same relationship between all the values. Right? This is kind of left and right, 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 left and right. Okay, but if you draw them like this, and we put these little numbers underneath, okay, you can see that if we take these stacked arrays and put them all right next to each other, right, this one array really holds the exact same information. Okay. Now if we wanted to do a breadth first traversal, it becomes very easy. We just march through the array from left to right. Right? So the order would be 42, 17, 50, 13, 24, 44. That's exactly the same order we would be traversing through here if we just go from left to right. And that's pretty advantageous if you're going to do a lot of breadth first type of work. Okay, turns out if you do have this kind of array-based tree, you can also do many of the same things you can do with a normal tree. So let's say we're at position 0 here. And what if I asked you, what's the position of the left child? Okay, so the position to the left of 0 looks like it's 1. And what if I asked you the position of the right one? Well, based on from our original tree, we know the right one's value is 50, so the index of the right one is 2. Okay, so for 0, we had a left value of 1 and a right value of 2. Okay. So what about position 2? This guy right here. What is his left and his right? Well, his left looks like was 5, and his right was the value 6. Okay. What about the index of 6? This one right here. This one has a left and right value of 13 and 14. Okay. And maybe you're noticing a pattern here. There actually is a pattern. So in general, if you're at a certain index, the left child will always be 2 times the position plus 1. Okay, so when the position was 0, 2 times 0 is 0 plus 1 is 1. That was the left. At position 2, 2 times 2 is 4, plus 1 is 5. When we're at position 6, 2 times 6 is 12, plus 1 is 13. And the right is similar. It's going to be 2 times the position plus 2. Right. So again, at position 0, 2 times 0 is 0, plus 2 is 2. At position 2, 2 times 2 is 4, plus 2 is 6. At position 6, 2 times 6 is 12, plus 2 is 14. Okay. So we can move left and right in this array-based tree just by doing that little bit of arithmetic. Now, in order to make this work, what we might want to do is we need this vector here for sure, or this array. And what I think we should do is have this array or vector be an array of pointers rather than actual nodes. So instead of nodes, I'm going to make this a vector of node pointers. Okay, something like this. Okay, and what we want to do, I think, is kind of make this large enough. We have to make the vector large enough to hold all the elements that could be in the tree. So in order to do that, we have to estimate the height of the tree and make the array big enough, and then we're going to actually fill the vector with null pointers to indicate that the tree is not holding anything. Okay, so if we have a tree with a height of, let's say, 3. So this tree has 3 levels. The height here would be 3. Well, a tree with a height of 3 requires 7 elements. Right? There's room for 1, 2, 3, 4, 5, 6, 7 elements. A tree with a height of 4. Remember, this tree had a height of 4. Well, here we require 15 elements. And if we were to add another element down on level 5, well, then we'd require 31 elements. Right? So we have the 15 that we have here, and then the next row, of course, we would have. Let's see. It looks like we'd have 16 more. Right, so the next row would have 16 elements. We go 1, 2, 4, 8, 16, 32, 64. Right, and that sums up to be 31 total elements. Right. So we can actually use the height to figure out how many of these node pointers that we're actually going to use. Okay, so it's basically you take the height, actually you take 2, raise it to the height minus 1. Right, so when we had a height of 3, 2 to the third is 8, minus 1 is 7. Tree with height of 4 required 15 elements, 2 to the fourth is 16, minus 1 is 15. And tree with a height of 5, 2 to the fifth is 32, minus 1 is 31, so there would be 31 elements there. Okay, so if we really want to make an array-based tree, we have to get an estimate of the height, create this vector or array of node pointers. And again, we use node pointers because not all of the elements in the tree are going to be used, right? And we can just fill them with nulls, and a null is a special value that will say basically that there is no piece of data at that particular position. Okay, then what we'll want to be able to do, of course, is to insert things into this array-based tree. And what we're going to do is we're going to use the null pointer. If we ever encounter a null pointer, that's going to be the point that we do the insert. Okay, so before I draw the picture, let's look at some code here. So this is going to be an array-based insert function. Okay, so again, we're going to pass in a piece of data to be inserted, and then we're going to call our insert helper, just like we did with a plain old binary search tree. So we pass in the data. You might remember in a binary search tree, we always start at the root pointer. Well, in this case, 0 always represents the root. Okay, 0 is the position of the top of the tree. Okay, so whenever we need to deal with the root, that's always just going to be the position 0. Oops. Okay. So basically 0 means the root. Now our insert helper, again, it's taking a piece of data and a position in the array. So the base case is when we encounter a pointer inside the vector that's null. And if we ever encounter one, then that's where we know we're going to put that node. Okay, so again, when we do our first insert, position is going to be 0, the root, and that pointer is going to be null. So we're going to store a new node at that position and store the data for that, the data that gets passed into that node. Okay. Now, if this is not true, if the array at some position is not a null pointer, well, we're going to do something very similar to what we did before. We're going to say, well, is the data we're trying to enter less than or equal to the current node's data? And if so, we want to recursively go left. And we know how to go left. It's just 2 times the position plus 1. If the data happens to be greater than the data at that position, we're going to go right. So we're going to recursively call the function and say 2 times the position plus 2. We know that's how we're going to go right. Okay, so let's go through that insert again. Okay, let me draw a picture this time. Okay, so I'm going to insert the exact same values. 42, 17, 24, 13, 15, 50, 44, and 46. Okay, so I know the height of this tree. The height is 4. So that tells me 2 to the fourth minus 1 is 15. I would need to make my array, or my vector, 15 elements long. And if I drew it in kind of this format, I'm going to have 1, and then 2, and then 4, and then 8. and I'm going to assume these all get set to null. So I need to create my vector of nodes, march exactly 15, march through and set each one equal to null. Okay, so now that I have this array-based tree, okay, remember what happens here. So we're going to call insert with all these values. Always start at position 0 or the root. Okay, so when we insert the value 42, right, we're going to start at position 0. We're going to call that helper. And we're going to see, is the array at position 0 equal to null? We know it is. So we're going to create a new node and store the data in that pointer. Okay, so this will actually point to a node that has 42 in it. Okay. Then next we're going to insert the value 17. Right. So again, we're going to start at position 0, and we're going to say, is the array at position 0 equal to null? Well, now it's not. Right? It holds the address of this node with 42. Okay, so we're going to see, is the data we're trying to insert 17, is that less than or equal to 42? We know it's less than. Right? So we'll call insert helper, this time taking 2 times the position. 2 times 0 plus 1 is 1. Okay, that is exactly this guy's left. Right? And that's a null pointer, so we're going to create a new node there with the value 17. Okay. When we insert 24, again, starting at 0, that's not null. 24 is less than 42, so we're going to go left by taking 2 times 0 plus 1. That's going to be an index of 1. That's also not a null pointer. So we'd compare, is 24 less than 17? No, it's greater than. So we're going to go right. And the way we go right is we say 2 times 1 is 2 plus 2 will give us the value 4. That is a null pointer here. So we're going to create a new node and put the value 24 there. Okay, 13, again, we'll go left. We'll go left here. We'll add 13. 15, we'll go left. 15 is less than 17, so we'll go here. Now we'll go to the right. So 2 times 3 plus 2 is 6 plus 2 is 8. So this pointer is going to hold the node with 15 in it. Okay, and then 50 is greater than 42. Here we have a null pointer. 50 will go there. 44 is greater than 42. 44 is less than 50, so we'll go left. 2 times 2 plus 1 is position 5. That's where our 44 is going to go. And lastly, 46 is greater than 42. It's less than 50. It's greater than 44, so we're going to go to the right. 2 times 5 plus 2 is 12. And that's where we're going to have 46. So we have all these pointers now. Again, another way to think about this, unstack them, put them all right next to each other. And now if we want to do any kind of breadth first work, we can just march through here. And anywhere there's not a null pointer, right? So there's a null pointer there, there's a null pointer there. Right. We could very easily set up a loop that just goes from 0 to 14. And if the pointer being stored there is not null, then we know there's good data. Okay, and we can just go left to right, from 0 to 14, do that check, and that's a really easy way to do a breadth first traversal. And you'll see this tree is exactly the same as the original tree. It just happens to be array based. And the only disadvantage, of course, is this is very similar to a safe array in that we're allocating room for things we're not always using. Right? So even if we went down one more level, we'd have to make room for 16 more pointers. So that is kind of a downfall of, or it's not a downfall, but a con of having an array-based tree is is we're always allocating a little bit more than we actually need. But the same was true of the safe array. Okay. So I kind of like this array-based tree. I think it's neat and can actually help us do things like if we wanted to print all the values in a tree form, where we can only print out left to right, top to bottom, it might actually help us to create an array-based tree and then march through the elements like that. So we'll talk about that in class, I believe.